I'm Josh Taggart.
And I'm Gavin Knudsen.
This is our final project video for ECE 3710 microcontroller hardware and software.
Our project is the O.R.E.O. That's the Orienteering Robotic Explorer with obstacle avoidance.
The O.R.E.O is a maze-solving robot that uses ultrasonic sensors to detect obstacles.
Now, let's get into how it works.
The O.R.E.O features two microcontroller boards, one for the stepper motors and one for the ultrasonic sensors and algorithm logic. To understand the reasoning for this, let me tell you a little bit about how stepper motors work. The stepper motors that we're using have 4 coils. And in order to turn the shaft in the center here, you need to energize each of the coils one at a time. In this picture, we're energizing this coil, so the shaft with this magnet attached will rotate towards it. For our robot to work, we need the stepper motors to be running continuously, and that requires the program to be continuously switching coils from one to the other. This presents a problem because if we want our robot to be doing any kind of computations or reading from sensors, we'll have to pause our stepper motors stepping in order to do those things, so the robot won't be able to move continuously. It'll have to stop and think and stop and think. We don't want that to happen. So to solve this problem, we split our thinking across 2 boards. Board number 2 will be continuously stepping through the motor coils. Board number 1 will be reading from the sensors and handling all the algorithm logic. Board 1 sends motor commands to board 2, such as move forward, turn right, turn left, and stop.
Alright, so the next step of the process is for the robot to see the world around it. Now, while you and I may use eyes, our robot actually uses hearing. And it's kind of similar to the idea of if you have a well, like this one, and you wanted to know how deep down the well is. You pick up a rock and you throw it down there, and you count how many seconds it takes to hear the sound of the rock splashing. The robot does something similar, except it uses ultrasonic sound waves, so sound waves that we can't hear. Now, this is what a ultrasonic sensor looks like. There's one side that's a transmitter and one side that's a receiver. So on this side, it'll send out a sound wave, and on this side, it's expecting to hear a sound wave. So the time it takes between when this is transmitted and by the time that it receives the echo off of something, that's how far away that object is. We have 3 ultrasonic sensors on our robot, one on the right, one on the front, and one on the left. And what we do is we alternate going between each of these sensors one at a time, detecting how far away an object is and seeing if there's a wall there. And it's through these sensors that this robot is able to see the world around it.
The objective of the O.R.E.O is to escape a maze. So it'll start inside the maze, and then the algorithm that it uses will help it to get out of the maze. We're using a simple right-hand rule algorithm to solve the maze. At every opportunity it can, it'll turn right. Otherwise, it'll go straight, and if it can't go straight or turn right, it'll turn left. So there are 4 different cases in our algorithm. Case 1 is an opening to the right. For example, let's say the robot's going this way, and it sees there's an opening to the right, it's going to turn right. Case 2, there's a wall to the right. So for example, if it's here, there's a wall to the right, we're just going to keep going straight. Our third case is a wall in front. For example, let's say the robot's going along here, it detects a wall in front, it's going to turn left. And let's say it's going this way, it detects a wall in front, it's going to turn left. It's going to detect another wall in front, it's going to turn left again, and it's going to end up turning 180 degrees, which is what we want. Our fourth case is there are no walls nearby, which means it has exited the maze. So when it comes out of the maze, it'll say, okay, there are no walls to the left, the right, or straight ahead.
Throughout developing our design, we went through several iterations and we made several changes from how we originally conceived how our design would work. One of the first ones was to change out the color sensor. We were originally going to have a color sensor that would detect tiles within the maze, and if it hit a green tile, then it would know that it was outside of the maze. We decided it would be simpler if we just used the sonar sensors to detect if there was walls around it, and that would lower the complexity by having one less sensor to worry about. It made for a more elegant design. Another change that we made was we were originally planning to implement a self-correcting feedback loop, so the sonar sensors on the side would detect how close or far away it was from the walls and self-correct so it was always in the middle. We realized that was far too difficult for this project, especially with how we ended up controlling the motors with the second board. That would make it far too complex. We decided that instead we would shoot for accuracy in turning and in moving forward, so that then we wouldn't have to worry about that and it could still navigate the maze without having this added complexity. Another thing is, as we talked about before, we introduced the second microcontroller board. Originally we were planning on only using one, but we discovered that using two made it a lot easier to integrate with the motors. And the last one was we were planning on using interrupts to take care of the sonar sensors. That would mean that the sonar sensors were on a timer and they would all fire at the same time. We decided that that wasn't the best because we were getting a lot of noise and a lot of feedback, and so we decided polling would be the best route because then we can make sure we're having one sensor at a time and we're getting more consistent data that way.
Now we'll take you on a journey through our development process.
And we'll show you how we got to the O.R.E.O that we now know and love.